phone down. Nope. Here we can make coffee. Good morning to all. And Mama says good morning as well. Say good morning, Mama. Say good morning. Okay. So we left off at, the homework was 80 BCD, if I remember correctly. So let's do that one, 80B. 80B is how many milliliters of 0.125 molar sulfuric acid are needed to neutralize 0.200 grams of NaOH. So today is Holy Thursday. Tomorrow's Good Friday, so I'm not going to transmit. And I'll see you again on, I guess, Easter Monday. Don't forget to pray. All the churches are closed, but we should be still praying together, asking God for mercy to protect us from the virus, and perhaps even more importantly, from the people who are trying to take over the planet. So the sulfuric acid is 0.125 molar. You're asked how many mLs are going to be needed. The NaOH is 0.2 grams. So you're going to find out how many moles that is by adding the mass of sodium plus oxygen plus hydrogen, which gives you 0.2 divided 39.999711 grams per mole. Equals 5.00036.128 times 10 to the negative 3 moles NaOH. Now, there's a 1 to 2 stoichiometry. So for every 2 moles of NaOH, you only need 1 mole of sulfuric acid, because sulfuric acid is diprotic and hydroxide only has 1. hydroxide group. So we're going to say times 1 mole H2SO4 divided for every 2 moles of NaOH. So moles of NaOH will cancel. And what we end up needing in moles of sulfuric acid is 2.5000, sorry, 18064 times 10 to the negative 3 moles NaOH. Using N equals M1V1, that's the N. So 2.500, etc., times 10 to the negative 3 is equal to 0.125 molar times the V1. So V1 ends up being 2.00014451 times 10 to the minus 2 liters, and you can convert that to milliliters by multiplying by 1,000, so that you'll get a final answer of 20.0 milliliters. If you guys could check in, just a reminder, so I can see who's been there. Okay, good. Bisola. Because I go through the list of people who have checked in, and I'll put you as present for that classroom, and I'll find a way to credit you for it. Adinakan Aldedayo. Who else? There's 7 people online right now. Oh, went back down to 6. Stella, okay. Good morning. I'm doing 480C next. So if 55.8 milliliters of barium chloride solution is needed to precipitate all the sulfate ion in a 752 milligram sample of sodium sulfate. Oh, sorry, I'm looking at C. That is C, sorry. What is the molarity of the solution? So 55.8 milliliters of barium chloride is needed to precipitate all the sulfate ion in a 752 milligram sample of sodium sulfate. So let's start by writing the equation. New dry erase markers, a lot harder to erase. They're not all created equal. So barium chloride is mixed with sodium sulfate to give barium sulfate, which will precipitate, plus 2 sodium chlorides. We're told that 55.8 milliliters of this solution was needed. We don't know its molarity. That's what they're asking us to find. And we're told that 752 milligrams of this stuff was titrated. So we're going to turn that into grams by dividing by 1,000. and then we're going to divide by the molar mass to find the number of moles that's present. So that, you have 5.29 times 10 to the minus 3 moles of sodium sulfate, and it's being titrated by 55.8 milliliters of the barium chloride solution. There's a 1-to-1 stoichiometric ratio between the two, so we simply find the same number of moles. The same number of moles of barium chloride is being delivered by that concentration, so we can say M1V1 equals this value of N. The M1 we're looking for, the V we know is 55.81 thousandths of a liter, and it's all got to equal 5.29, etc., times 10 to the minus 3. So M1 equals this divided by that, and you get 9.48775316 times 10 to the minus 2. And you're only allowed 3 sig figs, so you're going to say 9.49 of barium chloride. Next is problem D. It says if 42.7 milliliters of 0.208 molar hydrochloric acid solution is needed to neutralize a solution of calcium hydroxide, how many grams of calcium hydroxide must be in the solution? So 2 parts hydrochloric acid has to react with 1 part calcium hydroxide. Both of them are aqueous, obviously. The products are water and calcium chloride. There's 42.7 milliliters of hydrochloric acid with a concentration of 208 molar, 0.208 molar, and we're trying to find out how many grams of calcium hydroxide was necessary to neutralize it. So it's a M1V1 equals N type of problem. So 0.208 moles per liter times 42.7 thousandths of a liter is equal to 8.8816 times 10 to the minus 3 moles. But recall that there's a 2-to-1 stoichiometry here, so we have to include that. So we're going to say times 1 mole of calcium hydroxide is used up for every 2 moles of HCl we're using here, 2 moles of HCl. So the moles of HCl will cancel, and the value of moles we need is 4.4408 times 10 to the minus 3 moles calcium hydroxide is needed. And if we do the molar mass of calcium hydroxide times 40.08 for calcium plus 15.394 times 2 for the oxygens plus 2 times 1.00794 for the hydrogens grams per mole. I'll put the result here. It works out to 0.32, so you're multiplying this quantity by the contents of this bracket. So you're going to get 0.329 03965 grams of calcium hydroxide. You're only allowed 3 sig figs, so you say 0.329 grams calcium hydroxide is your final answer. Let's do another one that might involve some of the other skills you would need. So we've done a bunch of stoichiometry ones, solution stoichiometry, titrations. 496, it says, use table 4.5 to predict which of the following ions can be reduced to their metal forms by reacting with zinc, and it gives you a bunch of ions that you can test. Well, that's a single displacement type reaction. So whenever you have a single displacement reaction, you need to remember your activity series. Oh, he's back. He likes to stand behind the camera while I'm lecturing. Okay, so the activity series. Activity series is a good way of determining whether certain metals are compatible or not. Auto manufacturers have known for a long time that you should never mix certain metals. For example, if you mix iron with copper, you're going to rust your iron really fast. Hello from Italy. Mid-light fair. Hi. I'll write up the list for the activity series, which I know from memory. It goes like this. So the most active metal is lithium. It's got the highest oxidation potential, and also, interestingly, it has the lowest weight. So it's the least dense metal in the universe, but it also has the highest oxidation potential, making it very, very useful for batteries. Here's the activity series then. Lic, Ba, Ka, Na, Magal, Min, Zinker, Pico, Nisin, PBH, QEG, Hugpatau. So gold is at the bottom of the list, so gold is the least reactive metal, and that's why you find gold on, as an application, the best application for gold is as a conductor and as a coating on sensitive areas where you don't want the metal to oxidize. For example, the tabs in which you plug in your memory cards in your computer, all of those things are usually coated in gold to avoid oxidation and to guarantee a good connection between the computer motherboard and all the different cards. In fact, there's a whole industry thriving around recycling computers. People cut those little tabs off and they extract the gold. And gold is always in high demand for jewelry and coinage. Gold is so unreactive that you can actually find it in the elemental state in the ground. You can even find nuggets of it, especially if you go in places where the glaciers have crushed and destroyed rocks and also rolled them around. So whenever you have a moraine sitting on top of bedrock, that's where you're going to find a good chance of finding gold. And typically, because gold is one of the heaviest minerals, it'll go right to the bottom until it hits bedrock. So people who prospect for gold usually have to keep on digging down until they hit bedrock, and then that's where they'll find the highest concentration of gold nuggets. All right, let's get back to our question. So, sodium ions. So the question is asking, which of the following ions can be reduced to their metal forms by reacting with zinc? So the setup of this question is like this. If you have zinc in the metallic state, so meaning its oxidation state is 0, and you were to put it with an ion, and this, the first example they gave you is sodium, could you get this happening? Well, let's see who's higher on the activity state. Zinc is over here, sodium is higher up. The answer is no. You cannot do this reaction. This will not happen because sodium has a higher oxidation potential than does zinc. Look, you got to see this. Oh, okay, he left. As soon as I pay attention to him, he goes away. Oh, now he wants to go see mommy. Okay. He sees me talking, he doesn't know what to make of it, but he sits and pays attention. Look at plumbous ions. So you have zinc in the elemental state and plumbous ions. Which one is higher on the list? Here's lead, plumbous. Zinc is higher than plumbous, so this reaction can take place. The zinc will give its electrons to the plumbous ion, so what you will get is Zn2+, and the lead will be reduced to the elemental state. This one can happen. I'll do one more just for fun. Magnesium. So if you have zinc in the elemental state and magnesium in its oxidized state, can this reaction take place? Well, magnesium is here and zinc is there. Zinc is lower, no reaction. Can't happen because the magnesium will, the opposite reaction could happen. If you had magnesium in the elemental state with a 0 oxidation state and zinc was oxidized, you could make this happen. Oh, sorry. So that would be 0 oxidation state and the magnesium would become oxidized. Okay. The next one I want to try. How much time? We get 25 minutes already. Okay. Let's do a dilution problem. This is on. I've put this question on the final exam for several years, and I'm surprised at how poorly students doing it, because I've always thought it was an easy question, almost a giveaway, but evidently I was wrong. So, 498. It says a 35 milliliter sample of 1 molar KBr and a 60 milliliter sample of 0.6 molar KBr are mixed. The solution is then heated to evaporate water until the total volume is 50 milliliters. What is the molarity of the KBr in the final solution? So I'm going to write it all down for you because nobody could keep that in their mind. So you got KBr, and you've got another solution of KBr. One is 35 milliliters of 1 molar, and the other one is 60 milliliters of 0.6 molar. So you add them together, and then you heat it until the volume goes down to 50 milliliters. Answer is, what is molarity of KBr now? Okay. So, whenever you get one of these problems, the only thing you care about is concentration of solute over volume. So find the total solute, total volume, and then you can calculate your new concentration. Your total volume is 35 to 60, and then it goes down to 50. Actually, don't even care about that. Let's find how much the value of N for both of these. Add those two numbers together and then divide it by the new volume. That's the fastest way to do it. So you know that N is equal to M1V1. You got 1 molar here and 35 1,000ths of a liter. So that means you got 0.035 moles. Let's double check here. I don't want to lead you down the primrose path, as they say. 0.035. Yeah. So 0.035 moles of KBr contributed from this. This one also, you're going to use the same calculation, except this one is 0.6 molar and 61 thousandths of a liter. So 0.06 times 0.6 gives you 0.036 and equals 0.036 moles of KBr. Now you add all that KBr together because you've mixed the two solutions together. So 0.035 plus 0.036, 0.071. Should have done that in my head. That was embarrassing. 0.071 moles of KBr, and it comes to a volume of 50. So divide by 0.05 liters to get your final concentration. Because remember that molarity is equal to the number of moles over the volume. That's what you're doing over here. Divide that by 0.05, and what you get is 1.42 molar of KBr. Okay, it's a problem where you just have to remember the definitions of concentration, and boils down to this. Molarity of any solution is given by the total number of moles divided by the total volume. It looks like an overly complicated problem, but you just get down to the basics and then mix it all together. I'll give you one for homework. $4.99. Let's see if you can do that by tomorrow. I mean by Easter Monday. So that gives you a whole weekend. I'm going to give you 2 problems. I'll give you 99 and 103. I'll show you those 2 questions on the book. So 99 is here. Here's 99. And 103 is this one. Hopefully you can focus on that. Use it, look at it on a TV, and then pause it, and then you can do your homework that way. And I'll see you on Easter Monday. Don't forget to pray. I'll pray for you, and hopefully this is all going to end pretty soon. I'll see you guys.